This is a continuation problem in a true problem question in NCERT. For the above problem, the direction of the gravitational intensity at an arbitrary point P is indicated by arrow D, E, F, and G. So the above problem that this question is referring to is in the following two exercises, choose the correct answer from among the given ones. The gravitational intensity at the center of the spherical shell of uniform density. We solved this and we got this as C. Now, for this question, at any random point, suppose if this is a random point P, what would be the direction of gravitational field intensity? Is it D? Is it G? Is it F? Is it E? If you take the plane, if you take this plane, let us discuss this problem in detail because nowhere like a proper explanation is given for this. So this D is literally lying on the plane. So D is basically lying on the plane. Then even this G also is lying on the plane. So G is also lying on the plane. This E is exactly downward. E is vertically downward. So E is perfectly down. Now, if you look at F, F is at an angle. That means I wrote F is at an angle. So you can think like if F is in this way, we can resolve this F into two components. I will have some horizontal component. I will have vertical component also. Like example, suppose if this is the plane, and if I tell at this point we have F in this direction, and we can resolve this F into two components. One would be horizontal component, another one would be vertical component. Now, first of all, directly let me tell you, the answer for this is given as E. That means the author is telling the answer must be pointing downward. But let us see why the answer would be only E. Why can't it be F? Because most people think there would be some, this is like a center of mass. We'll identify center of mass would be somewhere here. So the net gravitational field might be pointing towards the center of mass. Remember, it is not necessary that the net gravitational field should always point towards the center of mass or anything like that. Understood? Both concepts are not exactly same. But let us try to find, because most people don't go for D or G. The confusion is between whether E is correct or F is correct. Let us see why this F is wrong and what is the logic behind it. To understand the logic behind it, we'll go with a detailed solution rather than trying to end it in a minute. Suppose if you have a sphere, full sphere, you take any random point inside the sphere, any random point. So if you select any random point inside a spherical shell, the net field at that point is zero. We have already studied this. So E inside a spherical shell would be zero. Why that is so? Right now I won't go for it in detail. You can think like because of a concept of a solid angle. If I just select this segment exactly in the opposite way, if we select one more segment, so there because of the concept of solid angle, these two segments would counterbalance each other. But right now I won't get into it. Just remember that if there is a spherical shell, the gravitational field inside the spherical shell would be zero. I'm representing gravitational field with E. So the gravitational field inside the shell would be equals to zero. Now we are going to use this logic to solve the problem for this hemispherical shell. Let us see how we are going to do that. Now imagine you have a hemispherical shell. So I'll extend this. This is the point P, some random point P inside this space. It is not lying on it. It is in the emptiness. Like this is a shell, right? So this point P is on the emptiness on one of the, like on the circular plane that is present. Now this point P, let us assume it has some kind of a, let us take this is the center of this. So this is the center of the spherical shell. Now, first thing we have to conclude is what will be the direction of field? Like the first question I will answer is, can it have tangential field? Like what do you mean by this tangential field? Like, can this point P have a one component, that is, I will draw an imaginary circle on this so that you understand it easily. So I'll draw imaginary circle on top of this circle. So this is another imaginary circle. Since it is an imaginary circle, I'll draw it with a different color. So consider this imaginary circle. Can this point P have a tangential component and a radial component of gravitational field? Can it have a tangential component and a radial component of this gravitational field? So that if it has both tangential and radial, then the net field would be somewhat pointing in this way. So let us see that. Suppose if I assume this P has a tangential component of gravitational field. Sometimes I'm calling it electric field because logics are generally same for both of them. So if it has a tangential component of gravitational field, imagine you have a small mass placed here, and you took this mass and it has a tangential component, and you kept on moving it on this circle. So it has tangential component and you kept moving on this circle. When you move it on the circle, it started from this point P and again reached the same point P. Understood? It started from point P and again reached the same point P. And when you try to find what is work done in this process, what is the work done in this process? For a very small displacement, the radial one does not contribute anything because work done is force F bar dot S bar. So what is the work done due to radial forces or radial fields? So the work done due to radial forces would be 0. So I can directly write due to radial field, work done equals to 0. Why work done is 0? I will tell you. Imagine the field is pointing in this way. You are trying to move in the tangential direction because in circle you will be moving in tangential direction, right? So I'll point it in another way so that you can understand this. This is a very tricky problem. Listen to this carefully. I'm drawing circle in this way now. Imagine this is the point P. Imagine this is the center. This is E radial, gravitational field radial, gravitational field tangential. What is the work done due to radial field? The work done due to radial field is 0. Why it is 0 is that if I take any small displacement in this direction, both of them are at 90-degree angle. Since field and this one are at 90-degree angle, so work done due to radial field will always be 0. But what about the work done due to tangential field? If I take a tangential field and if I move a body in a circle, so let me take this body, and if I start to move this body in an entire circle, I am moving it down. The field is also down only. I'm trying to move it down. The field is also acting down only. Since both are pointing out in the same direction, so we can write due to tangential, the work done dW is equals to whatever is the force, and you can see displacement and this are in the same direction into small displacement ds into the angle is 0 degree. So cos 0 degree. So I can write this as the mass into whatever is the field that exists. I'll take a small mass into whatever is the field that exists, E tangential into ds. This is, we are getting it as non-zero. Since we are getting this as non-zero, if I take this body and if I start to move in an entire circle, we get net work done as non-zero. Okay, now the question is, what happens if the net work done is non-zero? If the net work done is non-zero, where the net displacement is zero, that field is called as non-conservative field. We know gravitational field is a conservative field. Since gravitational field is a conservative field, gravitational field is conservative. Since gravitational field is a conservative field, the net work done over any closed loop must be equal to zero. Why did I go through all this explanation and everything? Because many people don't know this concept. That's why I explained it in detail. Or else, as soon as we know gravitational field is conservative, we should directly tell that the field cannot have any tangential components. It should only have radial components. If they exist, if at all they exist, they should only have radial components. So straight away, the final conclusion is that if this is C and if this is point P, if at all any field exists, it could be in radial direction only. Either it would be in this direction or either it would be in this direction. We cannot have a field in tangential direction. So finally, the conclusion is that if a field exists, on circular plane, remember I wrote the word if, circular plane, it cannot be in tangential direction. Because this is the property of a conservative force. Gravitational field is a conservative force. The same logic could be extended to electric fields also, and can only exist in radial direction. In radial. Okay. Now, in this radial also, this side and this side, you can take anything, it's fine. Now, let us assume there is a net attraction towards the center. All these are assumptions only. We still did not, because ultimately I will prove you that no horizontal field only is possible in a sphere. Imagine that this is the center, and imagine that this is my point P, some random point Q, exactly at equal distances I will take. So some random point P and this random point Q exactly at equal distance from the center. So based on the logic that we have discussed, so this P, if it has some force on the plane, that force must be towards the center. And if this Q, if it has some force, that force should be towards the center. If it has a force. Okay. Now I'll take this, Control C, I'll take a picture of this. I'll exactly place another plane and I'll complete it. Now, if I complete this, if I put a top on something on this, understood? Once I complete this, we have already studied in a full circle, in a full hemispherical shell, the net field at any point must be zero. But if I assume that there is one force in this way, there is one force in this way, and when I try to complete it, what are we getting here? We are getting that the net field is not equals to zero. Because by the symmetry, but we already know in a full spherical shell, it has to be zero. Two things we have done here. First, we have proved why it cannot have any tangential one. The second one, now I am telling it cannot have radial also. So here it cannot have radial field also. Why? Because if it has a radial field, and when I try to complete it, by placing this on top of this, we are having non-net field, but we have studied that the net field has to be zero. That means there cannot be any field in the radial direction. So if we have point P, and if I assume the net answer is in this direction, if I assume the net field is in this direction, when I resolve this into components, this component would be there and this component would be there. So if I take my original question and bring it here, so D, E, F, G, so I'll take it. If I assume this is the answer, and exactly at another point, we will have this as our answer. Now, if I control C and control V this, and if I flip it exactly, and if I place exactly on top of this, and if I try to resolve them into components, so their the component, their horizontal component, vertical component, horizontal component, their horizontal components would add up, whereas their vertical components would cancel. So we are getting a net field, and which is not possible. This is not possible. So what can we conclude? That means it cannot have any horizontal field on the plane. So the only possible answer that can satisfy this is that, suppose if we have is hemispherical one, and if I select this as my point, the net field can only be acting downward. If it is acting downward, even if I take another exactly opposite point here also, if it is acting downward, then when I try to complete it, both would exactly cancel each other. Any other direction that you take it, when you try to complete it, they won't cancel each other. This is a very, very detailed one, and it was a very lengthy video, but it is very important for you to understand what is happening. So what are the key takeaways? Since this is a very lengthy video, there are some major key takeaways. So that are, number one, if you select a hemispherical shell, every point on this, like you select any point, okay, on this plane, the net field will always be downward only. Understood? It is perfectly and vertically downward. No other field direction, horizontal field direction is not at all possible. Even in inclined field direction is also not at all possible. Why? Because if you assume the inclined field is possible, and when you draw a symmetrical image exactly and place it on top of this, you are getting a net field in this direction. But we already know for a full spherical shell, by the shell theorem, that the net field at any point must be equals to 0. So the only possible answer would be downward. But the only extra thing this video got stretched is that to prove that even the radial field is, the tangential fields are also not possible. I have took so much time to prove tangential fields are not possible, because if tangential fields are possible, there is a configuration that we can get here. Right now, if I explain it, it would be even more lengthier. But I hope you understood this. The correct answer for this would be E. Only vertical fields. Since only vertical fields and perpendicular to the plane is there, if a field, if the gravitational field is always perpendicular to the plane, we can call that plane as equipotential plane. I hope you understood how I have solved. Thank you.